Thank you.
Hello, everyone. Welcome to MACSMIN 2026. It's a great pleasure to introduce Professor John Helliwell, retired but formerly at the University of Manchester, who will talk about his recent book, Precision and Accuracy in Biological Crystallography and many other areas. So, John, over to you, please.
Well, thank you very much. And this is a contribution in celebration of Vitali's inaugural lecture. And it's a great pleasure. And thank you for the invitation. Yes, it's quite a long title, but that reflects structural biology today. And I'll elaborate some of the themes. So it's not advancing. Why is that?
If you click again on the slides.
Oh, just on the slide?
Yes.
No.
Okay.
So I'm trying page down. I'm trying on the mouse. Right click on the slide doesn't do anything.
Then you could try stop sharing and start sharing again.
Yeah. Oh, just a minute. There was an OK. No, that's not done it.
Yeah, so concerning video recordings, let me explain for our usual practice. So after the recording is saved, I'll check with the speaker. So sharing the video first only by link with the speaker and checking if it can be okay.
There we are.
Public.
Got it. Right. Anyway, so I don't know what happened there. So this is a table of context, and obviously not readable at this screen size, but I do try and bring out all the different aspects, and I've selected a few. The core ideas, basic physics, if you like. The impetus, where did that come from for this new book? And then I'll talk about the common conception. If you go to Google Images and type in precision and accuracy, you'll get a lot of dartboards with darts in different places on the dartboard. I hope people know what a dartboard is. Perhaps the ladies don't know, but anyway, hopefully it becomes clear. And then I will highlight what I think are high profile, at least in terms of the very widely read journals where I see errors. And the errors in not showing the precision and accuracy of the structure in our publications. And then with all this fabulous array of different methods, what can we do with combining methods and probes for achieving accuracy? And then I'll address why I chose to make this a teaching text and not a research monograph, because of course to a degree this whole topic is still a research area and developing still. And then I'll say some general things about the IUCR Oxford University Press book series, of which I was a member for 25 years and chairman for 6. So I'm very keen on the book series, and then some conclusions. I'll just get a pointer. Let's have a laser pointer. There we are. So the impetus. In about 1998, my collaborator, Durward Cruikshank, who retired in 1982 and joined with me in developing various things in macromolecular crystallography, particularly the Lowry method, but also he was generally interested in protein crystallography and what I was doing at the synchrotron. And he tested me with what seemed like a quite innocent question in about 1998. Why are there no error estimates on atomic coordinates in a protein crystal structure? And I confidently replied, "Oh yes, yes, we monitor the at the end of the refinement the agreement of the refined values against the dictionary covalent bond distance values and angles." And he said, "Oh, no. That is just a measure of how far away you are from convergence. And in any case, the non-covalent interactions are very important, and there's no dictionary for those. Obviously, hydrogen bond is typically 2.8 angstrom, but could actually vary over quite a range. And of course, in terms of globular proteins, then things like hydrogen bonding and van der Waals interactions and ionic interactions clearly are very, very important. So I was suitably chastised, and he went on with his own work to address this question. And the importance of it is if we look at some sort of quite typical diagrams in publication. So this one was from Nature in 2024, and they're studying a tuberculosis enzyme, ATP synthase, and they're interested in looking at the interactions between an inhibitor molecule at different binding sites to the enzyme. And here we have the, just to highlight at left side here, one of those sites. You can see the inhibitor and then the other sites. And they confidently mark on the black dashed lines, and here they are. The hydrogen bonds are represented by black dashed lines. There's no uncertainty in this. It's a black and white statement, hydrogen bonds. And they give also confidently to 1 decimal place these distances here. The center binding site, this is would be a almost really non-existent hydrogen bond. It's a very long distance compared with the typical 2.8 angstroms. And on the right-hand side, this third binding site, you can see what would be called a short, very strong hydrogen bond, 2.5 angstroms. But none of these, of course, show, and this is the point, obviously, you guessed it, there's no uncertainty estimate on any of these distances. And particularly vulnerable would be this middle one, where, if it, with the error, let's say it crept up to 3.8 angstrom as a possible value, it really would be non-existent, and it is wrong to say it would be a hydrogen bond with such confidence. And of course, the modeling by structural chemists, computational structural chemists in lead compound discovery or optimization, presumably would look at this and say, aha, we have something to work with here. But the point being, do you really? Now, in the past year, I can't claim it's the influence of my book, but I think there's a growing trend of something even worse, which is papers will show a figure and they will have this sort of thing with the side chains depicted and a molecule, and not even show any distances or putative hydrogen bonds. So it's really just to become a qualitative game. And I mean, that can't be right. That can't be what our experimental methods are reduced to. Anyway, to come back to Cruikshank and the late 1990s. So he produced this very interesting and at times very intricate analysis, which he published in Acta D. And you can see from this quote from section 10, so it's a long paper. Reliable sigma X values are needed for any discussion of non-dictionary distances between atoms in different residues, between protein and solvent atoms, or between metal atoms and their ligands. So that's a articulation of the point he made to me in our opening conversation. And he derived at the bottom line an interesting equation, which he called the diffraction precision index for the whole structure, with an average B factor, otherwise also known as the atomic displacement parameter. And on the right-hand side, we see the key players in determining the diffraction precision index. And of course, we know the overarching importance of the resolution limit in any study, be it protein crystallography or cryo-EM. And the Ni is the number of atoms of type I divided by P, the difference between the number of observations and the number of parameters in the refinement, and the data completeness of the diffraction data. All that is now almost all the time 100% complete. And so we have this coordinate, the possibility of an individual atom having an estimated coordinate error if we take the ratio of the atomic B over the average value and take the square root for consistency of the units, because the units of B factor are angstroms squared and the units of coordinate error are angstroms, of course. Now he validated his equation with this computer program method from George Sheldrick, the full matrix inversion, which is all the time used in chemical crystallography because they have the diffraction data going to a very high diffraction angle. And in this table here from his paper, you can see 3 examples, and the references are here. There's one from my lab, concanavalin A, which we took to 0.94 angstrom resolution, and a very good R factor, which is also in the equation, of course, here, the conventional crystallographic refinement residual between FOBS and FCalc over the mean FOBS. And you can see here the very close correspondence between the DPI sigma and the full matrix inversion value here, and that's true over quite a wide range of resolution limit, although you can discern a slightly increasing overestimate of the DPI against the full matrix inversion value as we see a worsening of the diffraction resolution. So we can evaluate with this approach if we think we might see an atom shift. So this is now taking us into another domain. It's not saying about individual structure, whether there's a hydrogen bond or not. It's comparing 2 structures, and is a differently placed atom, has it shifted significantly or not? And so this is an example from 2 of our my lab structures involving cisplatin binding and the histidine here, and 2 different PDB codes. And so we have a shift here of 0.4 angstrom. And of course, in time-resolved protein crystallography, we may see that sort of thing as a portrayal of genuine structural dynamics on light flash or something like that. But if we look at the atomic coordinate error here, then we can see that actually, if we insist on a 3 sigma value for the shift error, 0.4 angstrom, then we haven't got it. We're only at the 2 sigma confidence level. And so this sort of thing is really opens up a whole second domain of whether some structural dynamics is significant or not. And so I chose that as the motif for the front cover image of my book. Actually, I had quite a decent caption for what, and it's not exactly this one here. It's a different involving some rhenium protein studies I've been doing with colleagues in South Africa. But in fact, the publisher said, "Oh no, you only have a very, very short mention of the figure." And so I just say, I think it's on the back cover, that it was prepared by Francois Jacobs in South Africa, who's working with Dr. Alice Brink. Anyway, I think it captures the moment, which is, obviously there's some atoms shifted there. Is it significant or not as a shift? So with colleagues in Bangalore in India, we set up a web server so that people could, because of course in a PDB file you don't have the coordinate error. There is no error estimate, and you can put in the PDB code here, for example, or upload a PDB file. And this example here, we've got diffraction resolution, and we've got the overall calculated DPI. Now I've chosen this one because there's a different version of the formula using the R3, and so that is needed when the difference in the number of observations minus parameter goes negative, and at the worsening diffraction resolution, then that will happen. And so by a adroit maneuver by Cruikshank, you just ignore that number of parameters, work only with the number of observations, but instead use the R3. So obviously that is a bit of a crude approximation. And that begins to kick in at around about 2 angstroms or so, perhaps a bit worse. But anyway, this one here, it had to resort to the R3 version of the formula. Now, this illustrates a point that I make in my book, make it a key learning point, is that we shouldn't forget that this is the B and all, the B the end and so on of calculating these errors. We need to have different methods for calculating coordinate errors, and we can then compare the different methods. Oh yes, I forgot to mention that the web server also prepares the modified file. So on each atom, you have on the right-hand side here, the big arrow pointing at it, the extra column of numbers is giving you the coordinate error on an individual atom, which of course people need if they want to start calculating coordinate errors and the non-covalent bond distance errors, and also the structural dynamics.
John, could I ask if this error in red, is it for every XYZ coordinate? Is it one number for each of them?
So the overall value, I've gone back a slide, so the calculated DPI 0.391 here is for the average atom. And then, because the B factor of all the atoms varies, you can see the column here. This is the very important one. So for the higher B factor, 51 there, for example, that atom is going to have a bigger coordinate error. And then here's one at 32, and that's going to have a smaller coordinate error. But the average B is obviously even lower. So in fact, here we have a B factor of 17.8 with a DPI value for that atom of 0.32. And so I can't remember exactly what the average B is, but it's obviously somewhere above 18, probably 25 or something. So these are the estimates of the coordinate error on each and every atom.
And this estimate, this is an estimate for one standard sigma deviation, or? Or is
This,
it a mask?
this yeah. So the going back here, so I didn't point out. So here we have the sigma R. So we moved from an X, which is here, and it's one sigma on X, to answer your question. But then in addition, we are interested in what is in a given direction. And of course, we are assuming here isotropic movement, which is also not true. And we can model that when we're at the higher resolutions. So it's one sigma. And then in addition, I'm now taking the chance to point out we've moved from X to R. And so the calculated DPI there is on the R. And then this is switching back to this is sigma R on an individual atom.
Okay, so roughly speaking, it's one sigma for every coordinate of this particular atom.
Yeah, and of course the B factor is a very important determinant. So the B factor is a strong influence, as you can see here, and of course it's on the average B, it's a strong influence, and of course the physics formula, the root mean square, 8 pi squared u squared. If you take the square root of that, for the B value. So if you think of a B factor of 80 angstrom squared, then the root mean square displacement of the atom with a B factor of 80 is 1 angstrom. So that's a different way of cross-checking on the positional uncertainty of an atom. That simple formula. B of 80, it's a root mean square displacement of the atom of 1 angstrom. Because 8 pi squared is 80. Yeah?
Yes, thank you, John.
So let's return to some basics of physics. So is an individual method only capable of precise values but not accurate ones? Well, of course, in doing our experiments, we try and deal both with random and systematic errors. And for random errors, that is a list here. This is a paper from Sidney Abrahams in 1969, which is still valid. We need to count or have an exposure time for the diffraction that's sufficiently long to get a decent estimate of the number of X-ray counts in a diffraction spot. And then we have quite a long list of systematic errors, which we also try and deal with. And if we dealt perfectly with every one of these systematic errors, our method would be accurate as well as precise as possible by dealing with the random errors. Of course, the problem is that with the best effort in the world, you can't actually eliminate completely the systematic errors. And of course, a big one for X-ray crystallography is the X-ray radiation damage. That needs very careful as careful as possible management. But a probe like neutrons, of course, they're non-damaging to the sample. So neutron probing crystallography has a big strategic advantage in terms of no radiation damage. And of course, the B factor themselves on each atom we need to get an error estimate of those as well. I mean, you'll see in publications that the B factor itself is the error on the atom position. And the B factor is not that. It's actually the movement of the atom. And the estimate of the B factor will have an error, and that's different. So what about getting the error estimates on B factors? Well, if we think about what we do with our crystallography method, we have a probe, X-ray, neutron or electron at the left-hand side here, and the crystal sample is irradiated, and we measure the diffraction pattern with a detector, appropriate technology for the different type of probe. And so these days, we largely, but not exclusively, go to the central facility, the synchrotron or the X-ray laser, or the neutron, and the home lab is more dominated by people can still do a lot in the home lab with electrons. And we measure our diffraction images, and that really is an important moment in the history of a project. So it has the chance to be a historical version of record, that set of diffraction images, whether they come from X-rays or neutron or electron. And these days, the central facility, with the technology of storing data improving, they can now provide a digital data archive of the measured raw data. And over the years, different labs, different countries have their favorite diffraction data processing software. I put the one at the bottom here, Darsbury. We produce this Lowy software for the polychromatic X-ray work, and these others are largely only applied to monochromatic diffraction data. But obviously you could take the same set of diffraction images and put them through these different programs. And then, of course, when it comes to refining the molecular model, you've got different favored programs in these different packages. And then we publish in the different journals, and we have the appropriate databases on the right-hand side. So the peer review, when we submit to the journal, really should be the article, the model coordinates, the process diffraction data, and the validation reports. And the editor and the referee should look at all of those different as components of the peer review procedure before deciding, yes, they're all okay to be the version of record for the journal article and the entry into the database. But what if we compare the different softwares? And so here is a paper I published with colleagues in Utrecht and my student Simon Tanley in 2013. And we had 11 crystals. So we got 1 to 11 here on the horizontal. And then we compared the diffraction data B factor, the Wilson B factor as it's called, and the refined model average B factor. And we can see crystal 1 here, we can see quite a big difference between this program D-Star Trek, MOSFilm, and the Utrecht software Eval. And that's fairly similar for these behavior for these first 4 crystals. And then a different device was used for these others. And so we got crystal 5 and 6 and 7, 8, 9, 10, and these different softwares appropriate to the different instrumentation. And again, we see quite big differences between the different processing softwares. And then this 11th crystal here, behavior is different again. So what we're seeing here is the same in each of these 11 crystals, the same diffraction images, and we're getting different results. And so we can use this in a constructive way to say, well, we do have an estimate on the error on the value of a determined B factor of each atom. But of course, it's much more cumbersome to apply than getting the coordinate error from Cruikshank's formula, but it's still possible. So by using multiple processing routes with the same set of diffraction images, the final models can be compared to assess the spread of the B values, but also I emphasize the point here, you can actually get a cross-check of the atomic coordinate values. Each chapter I finish with key learning points, trying to do proper justice to this being a teaching text. So this is chapter 2. You can see the points that I'm making. And I think this parallel workflows method is really very powerful, but is not yet that, well, it's just not widely applied, but we have shown what can be done in our 2013 publication. Now let's have some fun with the dartboard analogy. This is from Google Images. So here at the left side, we've got several darts. They're centered on the bull, and the bull is truth. So we have a high accuracy, and there's a tight cluster, so it's high precision. Now this one, the second from left, we have this cluster of darts well away from the bull's eye, the center, so it's low accuracy, but they all agree with each other, so it's high precision. And then the third from the left here, we have nicely clustered around the center, so it's high accuracy, but they're rather far apart, each one, so it's low precision. And then, of course, on the right-hand side, we can show low accuracy and low precision. So this is very common on the Google images. You just type in precision and accuracy, and you get all these dartboard analogies. Now, in nature, as an experimentalist, we don't know where the bull's eye is. So we don't know truth as the bull's eye at all. So it's a tough situation that we face before we measure anything. And of course, the acid test is do different experimental methods agree? So this is a very interesting paper where an 80 kilodalton enzyme, malate synthase G, methods were compared, cryo-EM, and they achieved 2.9 angstrom, X-ray crystallography achieving 1.6 angstrom. NMR of the protein structure in solution is evaluated in a different way. They fit ensembles and deposit up to 20 different structures of one molecule. So this is a 2023 structure, and their aim was to show how well or not cryo-EM got the structure and the dynamics. And of course, it was quite topical at the time because 100 kilodaltons was kind of assumed to be the lowest molecular weight cryo-EM would work on, and of course 80 kilodaltons to achieve good resolution. 2.9 is important for lowering that molecular weight value to a value smaller than 100 kilodaltons. So we've got the protein on an electron microscope grid. We've got the protein packed into the crystal. We've got the protein in solution. So if you do the comparison of each model, the pairwise root mean square deviation, there's two molecules in the asymmetric unit here against the cryo-EM. And then a different structure here, you can see the slightly worse resolution limit, so it's a slightly worse pairwise RMSD. But the NMR, the protein in solution, is really quite different, nearly 4 angstrom for the RMS. Now, NMR on such a big molecule is struggling for the number of observations, but also we have more flexibility given for the molecule when it's in solution. And so if you look at where the differences are, if you look at particularly the loop regions, you will see there are places where there's quite different conformations. And in this loop here, for example, the two methods on the left and the middle here compared to here, the assignment of beta sheet is not made. Whereas here you can see there is a bit of common beta sheet compared to these other two methods. So this is a very telling comparison and shows up the limitations of working in Crystallo. And so we have to be aware of that when we extrapolate from the crystallography or indeed from the molecule on the cryo-EM grid to what happens in vivo. And so that shows up the limitations of a single method. Now, how might the cryo-EM people get an atomic coordinate error estimate? And so it's possible by splitting the cryo-EM images into two halves and fitting the model to each one of the two. And then you compare the so-called half maps fitting, and you can get an estimate of the coordinate error. And of course, at the end of the day, you can combine the two halves to get the final model, because you want to use all of the images to get the best model possible. But you can, as I say, get this half maps fitting for the cryo-EM estimate of each atom's coordinate error. This, like the Cruikshank DPI, is not, let's say not yet endorsed by the PDB. So the user of a PDB file is really not being guided at all by the thinking about the atomic coordinate errors, or indeed the error estimate of the B values in crystallography. It's dominated by the validation report, which is very useful for general things, but it's not going so far as giving us, in the end, what we really need for assigning hydrogen bonds or for monitoring atom movements being significant or not. We can combine methods, and this is a very ingenious one from solution scattering involving SACS, X-ray and neutron sands, and UV visible spectroscopy. And Professor Unruh and colleagues at the Institute Larry Langevin, here you see a conventional X-ray source beam entering on the left here. Here's the sample. The neutron beam comes in perpendicular, and we have the detector here. The wavelength of the neutrons is much longer than the X-ray, so you can see the diffraction angle has increased accordingly. And then if we zoom in, so the middle one here, we're zooming in, and even closer, we can see the UV visible spectrometer. So that is then simultaneously getting three different probes onto the same sample. That is a very ingenious development. So why a teaching text? I need to wind up because I'm running out of time, and not a research monograph. Well, it's not common practice to have atomic coordinate error estimates, so perhaps it should be a research monograph. But then, as Cruikshank forcefully put it to me, it should be common practice, and therefore it should be a teaching text. So I deferred to Cruikshank's definitive statement at the beginning. The book series, with colleagues. I have published one research monograph, which is shown here, and we have the green text is the research monographs. The orange ones are the teaching texts. The series, I'm short of time, but there's a very good range of achievements over the now nearly 30 years of its existence. And what does the IUCR do with the income? Mainly the income from journals is the dominant factor for doing good works around the world. But the books have also contributed a decent quantity of towards student bursaries. Website. I'll be sharing the slides as well. I'll put the slides on Zenodo. So here's the content split into two halves. It's wide ranging. I've only brought out a few of the themes. Another big theme is the IUCR style round robin project. The same sample or type of sample is passed to different labs with the same apparatus to see how the results compare. I also have brought in simulations and predictions, which I think are very important and interesting today. And of course, lurking behind everything is our prior knowledge. And that's where I tried to defend myself with Cruikshank. Initially, we can always compare with our covalent bond distances and angles in the dictionary. So we have Bayesian reasoning. I put that into an appendix. So we need standard uncertainty estimates. We can check reproducibility of a study if we have the data available. And these days, the power of computing and the power of measurement, we can measure more quickly, we can analyze more quickly, we can also do replicates quite straightforwardly. And I commend to you this very good report from the US National Academy of Sciences, Engineering and Medicine, reproducibility and replicability in science. It's really a fabulous report about 5 years ago, I think. And then with my work with IUCR and the importance of being able to preserve raw data, the trust in what we do can go up. And we've got our various measures, reliability, reusability, fair and fact. I've not gone into details of those, but this is our version, if you will, of the very general US national report. So with that, thank you, and I hope that contributes to the festivities of Vitali and his inaugural lecture. Congratulations again, Vitali. Thank you.
Thank you, John. Thanks a lot. Okay, I'll first stop recording.